Hi there, Mrs. Thompson here, and we are going to do part 2 of drawing Lewis structures. So if you did not watch part 1, please make sure you go back and watch part 1. Okay, the first part of today is looking at resonance structures. So what are those? Resonance structures are when you have a Lewis structure that can be drawn in more than one possible way. And so here it says resonance structures occur when more than one Lewis structure can be drawn. This often occurs when you have double bonds or even triple bonds, and it's not equal to the number of outside atoms. So you see this little example here, you see a double bond right here between carbon and oxygen, but not a double bond here. And so what ends up happening is you get this double bond flip-flopping, or resonating is what we call it now, from this oxygen to this one. Says when resonance structures can be drawn, you have to show each possibility, and you have to show arrows to show that those electrons are changing. They're resonating from one oxygen to the other in this example here. Notice how that double bond is not resonating on the hydrogen, and that's because hydrogen doesn't have the ability to double bond. It can only form one bond and then it's done. Okay, so we're going to do an example with resonance, and you'll do some in class. So we have O3. Each time I do these, you probably should be figuring out the number of valence on your own. Pause it, do that before I show you. All right, so we have 3 oxygens, and each one, it has 6 valence electrons for a total of 18. Okay, we have 3 oxygens, so how do we arrange that? We're just going to put them in a line. Okay, one of these oxygens is a central atom. Okay, so let's see, in terms of our steps, I have them here. We count the valence electrons, done. We figure out the central atom, since we have 3 oxygens, just oxygen. We draw single bonds to the outside atoms. So here we go, single bonds to the outside atoms. Perfect. How many electrons did I use? Well, I used 4. Okay. Subtract, I get 14 electrons left. Next step. Fill the octet for the outside atoms. So 6 here, 6 here, that's 12. Okay. Subtract, I have 2 left over. All right, number 5. If electrons remain, add them to the central atom in pairs. So we have 2 left, we'll put them on the central. And then we check, has the octet rule been obeyed? Well, this oxygen has 6, 8, and this one only has 2, 4, 6, so not obeyed on the central atom, but yes on the outside atoms. Okay, so when that happens, we steal. Problem here is I have 2 options. I can steal from the left oxygen, or I can steal from the right oxygen. And as soon as I do that, like I steal from the left, put them here, make that a double bond, then each of those oxygens has an octet. The central atom has an octet, the outside atoms each have an octet. I could have also stolen from the oxygen on the right-hand side, so to show that it's a possibility to do that, you actually have to draw both. All right, so we're going to draw the other version with the 2 electrons being stolen from the right side. Okay, to show that the electrons resonate from this oxygen to this one, we're going to put that double-headed arrow, which I've already done. And just so it doesn't get confusing, let's go ahead and put a box around both of those so we can show that this is our 2 resonance structures, and the top one is just our in-between stages. Okay, in this animation, what you see is you see the electrons traveling, and you see them resonating from the oxygen on the left to the oxygen on the right. And so how did scientists figure out that this resonance exists? Well, they measured the bond length between one oxygen to another. And so when you normally measure, you find that single bonds are the longest, and then double bonds get shorter, and then triple bonds are even shorter. And so what they found was, well, they thought maybe if one side is double bonded and the other side is single bonded, that the side on the left should be longer than the side on the right. Instead, they found that they were equal lengths and that they weren't the same as a single bond or a double bond. They were in between. So we found they're like a bond and a half. So we figured they resonate in between. Okay, let's try this one. We have a polyatomic ion. Take a second. What is that? Okay, hopefully you said that that is carbonate. All right. So let's figure out the number of valence. Carbon has 4 valence. We have 1 of them. Oxygen has 6 valence. We have 3 of them. And that adds up to 18. What about the charge? Remember, when it's negative, it's because it has gained those negative electrons. So that's going to be a +2. And altogether, 24 valence electrons to work with. We'll decide the central atom. That's got to be carbon, and the oxygen's all around it. Draw single bonds to the outside atoms and subtract. That's 2, 4, 6, leaving us with 18 valence electrons. Okay, let's put them on the outside. Okay. 6 times 3, that's 18, leaving me with nothing left. Unfortunately, my octet rule has not been obeyed because carbon doesn't have an octet, my central atom. Anytime it doesn't, then we got to steal. It only needs 2 more, so which oxygen do I steal from? Whenever you have this decision, you should be thinking it's a resonance structure. So let's just steal from this one. Put it here. Oh, I'm carried away there. So when we do that, when we steal that 2 valence electrons and make it share and form a double bond between the carbon and the oxygen, then we have an octet on the carbon, an octet on each of the oxygens. And so since we could have stolen from either the left, the bottom, or the right, then we have to draw all 3 possibilities. So it looks like this. Oh, and you also have to put brackets and the charge, because this is a polyatomic ion. So notice in this structure, we've got the double bond on the right, then the double bond on the left, then the double bond in the bottom, and we have the double-headed arrows in between. Sometimes books will draw it this way, where you have a dashed line that shows that this is resonating. But we're not going to do that. You're going to stick with this one. So don't draw that bottom one. All right. Last part of this is the exceptions to the octet rule. There are 3 that you need to know. One is electron deficient. Deficient meaning not having enough. So it would have less than 8 valence electrons. The second is expanded octet, where we have more than 8 valence electrons, and these are going to be on the central atom only. And then the last one is what do you do if you end up with a compound that has an odd number of valence electrons? These are very rare, but they do exist. First one, let's find out what kind of exception it is. This is BCl3. So boron with 3 valence electrons, chlorine with 7, 3 chlorines though, adds up to 24 valence electrons. So we'll put boron in the middle, chlorine on the outside, draw single bonds to the outside atoms. That got rid of 2, 4, 6 valence electrons, leaving me with 18. So then 18, I've got 3 chlorines. Each one can take 6, so that's 18. That means I have none left over. That's 0. Okay. All right, so normally, anytime I end up with 0 and I look for my central atom to have an octet, it's supposed to have an octet, so I would steal. Unfortunately, boron cannot do that. It just doesn't have the orbitals to accommodate that. Remember, it's really close to helium. And in terms of noble gases. It only has 3 valence electrons that it can share, and if you try to force it to do something else, then it just won't work. So we call this electron deficient. You need to remember electron deficient atoms are things like boron, beryllium, and aluminum. Every once in a while you get aluminum as being your central atom, and even beryllium as being a central atom. And when you do, even though these are usually metals, they can actually form covalent bonds because they bond with things that have very similar electronegativities. They cannot obey the octet rule. They just simply don't have the orbitals to do that. And so you end up not stealing. You leave it just as is. Okay. There's a calculation that we can do to prove this. It's called formal charge. We may or may not do this in class. But just note, boron, beryllium, aluminum can't follow the octet rule, just like hydrogen can't. And when that happens, you do not steal and make double bonds. You leave it alone. All right, let's try the next one. All right, here we have Zenon Tetrafluoride. Every time I show this one, students are like, that's a noble gas, and noble gases aren't supposed to form compounds. They actually can. They are unreactive, and those compounds are rare, but they do actually form compounds. All right, so let's figure this out quickly. I'm adding up the valence. I end up with 36. We'll put xenon in the middle. 4 fluorines on the outside. Single bonds to the outside atoms. Just got rid of 2, 4, 6, 8. And that leaves me with 28 valence electrons. Okay, this is where counting and subtracting really comes in handy, because if you don't do the subtraction part, you'll end up just saying, okay, well, let's put all of them on the outside and I'm done. But that's not true. If I count these, I've only used up 6 times 4, 24. Okay, I've used up 24 valence electrons. Wait a second. If I subtract, I have 4 more left over. Okay, well, what do I do with those 4? Well, normally, if we have extras, we put them on the outside, the central atom. So let's do that. Oh, here's a little statement. Let's just go ahead and do that. I'll discuss that. So I put them on the central atom. Notice I put them in pairs. You always do that. You don't spread them around. You keep them in pairs. And now xenon has more than 8. It's what we call an expanded octet. Okay, so it has these extra orbitals that can do this. And there are only certain elements or nonmetals that can do this. These are nonmetals that are from period 3 and below that can hold more than 8. And it's only when they're the central. You don't try to do that when they're the outside atoms. Okay, so central atom has 12, called expanded octet. You'll run into this most often with sulfur and phosphorus being your central atom, and then xenon. Okay, but like I said, anything from period 3 and below can do it. All right, last exception, and that is NO. And so we have nitrogen, and we have oxygen, and it adds up to 11. Okay, central atom. Well, this is NO, so there's no central. We just put them together. So NO. Okay, we draw a single bond. Takes up 2 electrons, leaving me with 9. So I'm going to go ahead and just start filling them on the oxygen. All right, that's 6. And that leaves me with 3 left over. Okay, I think that happened at the same time. Yes. Okay, sorry about that. So, leaves me with 3. I put them on the nitrogen. And now I have no more. Down to 0. Okay, so now here's where we start stealing. Okay. There's also something odd, which is that there are an odd number of valence electrons. So notice nitrogen has that one little lonely electron at the top. We call this the odd number exception. We still have to try to make it have as close to an octet as possible, so we'll do that. So we'll take these two, put them here, and we'll form this. Let's look for octet. Nitrogen has, actually let's look at oxygen first. It has 2, 4, 6, 8. Okay, that has an octet. Nitrogen has 2, 4, 6, 7. It's as close to an octet as it's going to have. Actually, what ends up happening with this is it actually will go and form, we call it dimerize. It'll actually bond with another one of these and form a new molecule, which will be N2O2. But we're not too concerned about that. We just have to know it's an odd number. We leave it like this, and that's it. Please bring questions to class.